Physics, as it is practiced and measured, operates within a strict subset of reality. We observe the five-dimensional coherent state space, denoted as S₁. It constitutes the observable geometric bulk of a much larger system. This observable bulk is defined by 5 coordinates: 2 phase strain components tracking the divergence between recursion partners, 2 recursive coherence retention functions measuring memory over time, and the integer representing the recursion depth or nesting level. But the mathematical architecture spanning Addenda 13 through 20.6 leaves 3 persistent gaps. First, the spinor channel, activated during the twist bifurcation, requires specific coupling functions, known as JJ, to govern symmetric phase exchange, circulation, and asymmetry. The current S₁ framework proposes these functions, but cannot derive them from first principles. Second, the explicit matrix field implementation of this spinor channel remains pending. Third, and most visibly, the framework has not yet derived the numerical values of dimensionless physical constants, specifically the fine structure constant, alpha, and the proton-to-electron mass ratio. These gaps specify a structural boundary. S₁ cannot represent the fundamental reality. The recursive torsion Lagrangian and the zero divergence vector lock matrix require independent parameters that S₁ simply does not contain. The 5-dimensional observable universe is merely the projected face of a complete 12-dimensional state. This diagram defines the 12-dimensional S₂ fiber bundle across 3 layers. The S₁ bulk governs observable phase strain. The spinor fiber activates coupling functions when recursion partners become distinguishable. The substrate layer contains observer alignment, torsion memory, gradient, and lambda, the source of particle mass. This exact coordinate count is independently corroborated. Grant's harmonic solid projection theorem approaches the geometry from a separate mathematical framework and arrives at the identical conclusion. The system reaches a maximum recursion depth of 12 before returning to singularity. The convergence of field-theoretic and geometric methods establishes a clear baseline. 12 independent coordinates are the absolute prerequisite to specify the full state of a coherent system immediately prior to bifurcation. In the 2-dimensional phase plane, the lock matrix requires phase states to quantize at 60-degree intervals. When extended into 3 spatial dimensions, this 60-degree condition exclusively generates the icosahedral symmetry group. The icosahedron is the unique Platonic solid where the golden ratio, phi, emerges not as an approximation, but as an exact algebraic coordinate of its structure. The icosahedron has 12 vertices, 30 edges, 20 faces. V minus E plus F equals 2. 12 minus 30 plus 20 equals 2. The solid angle subtended by each face gives omega F divided by 4 pi equals exactly 1/20th. 20 faces exactly partition the sphere. This is a structural identity, not a numerical coincidence. This geometry directly maps onto the field dynamics. The 5 independent zero-divergence vector lock conditions correspond perfectly to the 5 triangular faces that converge at every single vertex of the icosahedron. To simultaneously satisfy the ZDV lock conditions in the coherence phase space is to fulfill the Euler characteristic in polyhedral language. Topological closure is the exact mathematical equivalent of a locked coherent state. This blue histogram displays the results of a blind computational trial. To test if the icosahedral symmetry alone could generate fundamental physical parameters, 136 geometric candidates derived from the 60-degree quantization were plotted against 16 known NIST physical constants. The results established a rigorous baseline. Out of 136 candidates, exactly 0 natural matches were found that carried a mathematical complexity under 4 and an error rate below 0.1%. The search for the fine structure constant, alpha, yielded a mathematical expression with a 0.034% error. However, this expression required a complexity score of 8, relying on 4 independently chosen parameters. This is a post hoc mathematical fit, not a structural derivation. The results for the proton-to-electron mass ratio were equally definitive. The closest purely geometric match was phi to the power of 16, which carried an unacceptable 20% error margin. This null result is a structural proof. It demonstrates mathematically that physical constants are not simple, freestanding geometric combinations. Deriving their true values requires navigating the Lagrangian evaluated lock potential. The failure of phase 2 was caused by a grammar mismatch. The computational trial attempted to compare shadow grammar values against shadow grammar candidates. This visual represents the true location of the constants. Measured parameters like alpha or the mass ratio are not intrinsic real numbers. They are two-dimensional projections cast onto the observable O2 measurement axes from a higher dimensional source. To find them, we must shift to the substrate grammar. True constants are specific phase positions on this theta recursive structure. Alpha is the sign projection of its phase position. The mass ratio is the quotient of the proton and electron lock potentials at their respective conic coordinates. These coordinates advance along a strict harmonic series, where the next phase position equals -1/2 of the previous position. When projected out into the real number shadows of standard physics, this recursion translates its incurrence independently observed pattern. The next constant is the inverse square root of the prior one. The 19 free parameters of the standard model are fully determined Baggis geometry. Their apparent randomness is simply the triadic shadow produced when a 4-node quadratic substrate is projected through a phase-limited observer. The objective of phase 3 is to implement the inverse projection operator. It transforms the real number values of our observable universe back into their true substrate phase positions on the 12-dimensional manifold. The completion of this derivation is governed by a strict publication gate. It relies on a single condition: 0 free parameters. To clear the gate, the mapping must prove that all 16 NIST constants perfectly satisfy the theta recursion function to within 1/100%, placing all constants on the exact same conic manifold. Furthermore, the derivation of the proton-to-electron mass ratio must calculate to exactly 1836.15267343, evaluated strictly through Euler-Lagrange standing wave solutions. Addendum 21 maps the required coordinate transformation. It establishes the exact mathematical benchmarks that the subsequent Addendum 22 must meet for formal publication. This visualizes the projection architecture. Physics operates within the two-dimensional shadow grammar on the left. 10 fundamental dimensions casting these shadows remain invisible. The observer dictates this boundary. Approaching the twist threshold reorganizes the state space, briefly revealing the full 12-dimensional architecture before resetting. The empirical proof of this architecture runs on 2 parallel tracks. Phase 3 supplies the pure theoretical computations derived from the Lagrangian. Resonant modes on physical cymatics plates provide empirical measurements of this geometric scaling. The convergence of physical data with mathematical prediction provides the ultimate confirmation. The complete topological framework, the null result methodology, and the formal publication criteria are detailed in ODTBT Addendum 21, accessible via the DOI provided for peer review.